Now, our work in Extension 2 on volumes follows on from what we did with our work in 2 unit on volumes. Now, the first part is following on from exactly from what we did there with the volumes by slicing. Now, the idea is that when we take a volume and rotate it, or curve or an area and rotate it around an axis, what we get is an idea that we can slice through this curve and get a cylindrical disc from it. And we did this in the 2 unit. That's how we started to attack those. We got the formula pi y squared dx. Now the idea there is that we're taking a cylindrical disc and getting those discs and sewing them together. So what we want to do is take a curve, slice it, get an example, one of the discs, but that would just be representative of taking more and more discs. The more discs we take, the better our integral, better our approximation to that volume would be. And if we get the idea that if we take one of those discs and we slice it through, and then we get our formula for that disc, so we get a formula for the disc, and then we start to sum those discs, so between two values, and that thickness of the disc, so our disc comes out with a thickness every time, and that's where our thickness is, our change of x. And as that thickness starts to approach 0, so the discs get thinner and thinner, we obviously get more and more discs that'll fit between two values, and the sum of all those discs as the limit approaches 0 of the thickness of the disc, starts to give us an integral. So that's where the integral starts to come from. Now we're not going to write this down every time. We're quite happy to go straight to our integral there. But this is the idea, that we've got these cylindrical discs that are going to occur. And as you can see with this one, because it looked quite thick here, it's going to have an overlap of the actual volume. But the thinner they get, so the closer delta x here, the change in the value of x, so the thickness of the disc starts to become closer and closer to 0, those discs start to look thinner and thinner, and they start to be put together. So better to give us the volume. So the idea with a cylindrical disc is that, well, we're getting a small cylinder. So as we get a cylindrical disc, which means the volume of a cylindrical disc, all those discs, would be the area of the face, which is a circle, times the height of the disc, which is delta x. So the cylindrical discs are always going to be, if it's rotating around the x-axis, pi y squared. So we get the volume formula pi y squared delta x, or pi y squared dx, as it's going to be, which is what we had in the 2 unit course. And we do a substitution of 1 minus x for y, because y plus x was equal to 1. That's the function we're taking. That's the curve we've got this time. So we can rotate and we get y in terms of x. So the idea there is we always get it back in terms of what the delta x would be to do our because that's what comes down to integral. Our delta x becomes the dx, so the change in x. And once we get to the function here, the integration is usually the easy part. The hard parts in these problems, the volumes, is usually getting the function in the volume formula. So if we try to go through and do this way, get our diagram of our cross section, so we can get our area of our cross section, which can then lead to our volume formula, and then that will again lead in turn be able to get the integral between, and because the integral value is usually pretty easy. And then we're able to integrate and get our answer. So this time we've got a function y is equal to x squared. Again, it's rotating around the x-axis, so we're getting a change in x values as we move from left to right on our values. So our area then would be pi y squared, and y is equal to x squared, so we're able to do the substitution into both the area and the volume formula. And then we get our sum. Limit is at delta x approaches 0, becomes integral of pi x to the power 4 dx. And then we're able to put that into play and get our integration. Sine of x, so the functions we take are going to be varied. The integration techniques we use, it's going to depend on what the function we have, Most of the time the integration's easy. Sometimes you might have to use some extension 1 or extension 2 techniques. Might have to go integration by parts or partial fractions. Just depends on the function itself. But most of the time it's pretty easy. So sine of x, rotating around the x-axis, we've got a thickness of delta x. So our cross section again would be pi y squared, and the volume pi y squared delta x, and y is sine of x. And this is where we're going to have to use our extension 1 techniques, because sine of x can become 1 minus cos 2x, and then we can integrate. So that's that's the only hard part for that integration. And this question we've got x squared plus y squared. So the first quadrant of the circle, so x is greater than 0, y is greater than 0. First quadrant of the circle gets rotated around the x-axis. So our cross section would be a circle. Area formula pi y squared, and the volume pi y squared delta x. And the y squared becomes 1 minus x squared here. So we're not doing too much, because what we can do with this function is say, well, manipulate that. That gives us y equals 1 minus x squared. So there's our curve, just in putting y in terms of x, which means we can do that simple substitution. Don't worry about taking the square root and then squaring it again, and then between 0 and 1 we're able to put our integration in and be able to do the integral and get down to 2 pi on 3. So have a look at the technique we're using. Every time we do these questions, we want to try and do the same thing. We want to get our area and our volume, but we need our cross section, and we need a good idea of what our cross section is, because a lot of time if it's a circular disc, we want y to get our area, because so the radius is going to be important in a lot of cases. In these ones it's pretty easy because it's just rotating around an axis. They're going to be the easy ones. But be careful, make sure you get your cross section every time, whether it's a circle, whether it becomes an annulus, whether it becomes a square, a rectangle, a triangle. We will face all those different types of cross sections, and then we need to get volumes for those figures from that different cross section. And it's usually not too bad, because it's just multiplying by a thickness in that cross section, because they'll all be prisms. But the idea is that we make sure we get our volume there from our area, and we get our correct cross section. And a lot of times that's going to be the hard part, is making sure we get our correct area, which leads on to our formula. And the integration usually takes care of itself in that case. So be really wary about making sure our problem solving skills are able to get us that correct area in a lot of these questions.